Good morning. I have the pleasure of opening this, I don't know, do you still just call it summer? Let's say autumn school. I'll talk about model theory and definability. So the organizers asked me to give an introduction to model theory. And I thought about what I would want, what I would want someone who has an interest in model theory but hasn't got any formal education in it, what I would want them to know in 5 hours. So that's what I'm trying to do. In particular, this means if you're a researcher working in model theory, you're not my target audience. And if you're a bit bored, that's a good sign in my course. Okay, so the idea is that I give a fast-track introduction to model theory, or model-theoretic methods mostly. I'll introduce 3 basic methods and then try to, for each of them, give uses in number theory and give you further reading on, because obviously I will not be able to cover every proof in every detail. So, okay. And then in the final lecture, because when I then checked on the HIM website of the school, it said, and they will also comment on, current research. So that's what I reserve my 5th lecture for. Maybe, from lecture 4.5 onwards, let's see how I get on with my plan. But okay. So the plan for the lectures is first an introduction to first-order logic and the compactness theorem. Then quantifier elimination. So our first method is compactness. The second method is quantifier elimination. The third method is definability. And then we'll apply several of those in different settings to talk about definability of henselian valuations. So you see, in some sense, maybe there's definability of henselian valuations 1 and 2 because I have 5 talks, but I don't think the topics will align exactly with the endings of each talk. So let's see how we get on. Okay, so first, I start with introduction and compactness, and so I start with what's first-order logic. And I'm hopeful that many of you have seen this before, but so what I cover first is in the book of Tent and Ziegler, a course in model theory. What's called chapter 1, the basics there. And I don't know whether we can make a repository somewhere where even copyright protected PDFs can be stored. Philip is nodding, so that if you really want to do the reading, I would have I can supply the PDF. Okay, so first, I need to talk about languages and structures. So, a first-order language L is given by a number of symbols, sets of symbols, namely first a set of constant symbols, so a priori, a language is a purely syntactic notion, and a set of constant symbols has, they're just a set of things labeled constant symbols. They have no meaning yet. A set of function symbols. I'll try to write things out at the beginning. Each with arity. Where the arity is how many, where the arity later will be how many things you plug in into a given function symbol. A set of relation symbols. Each with arity. And then as part of, and for me, I put this into the formal definition of a language. So there's the so-called logical symbols, which are in every language, namely a binary relation, equality. And sometimes I try to do this at least at the beginning in order to differentiate the equality in the formula or in the language from the usual meta-mathematical equality. I write a dot over it. A set of variables. I take one variable for each natural number, and of course later I also write x and y for my variables and ignore that I've called them vi. But then connectives and or not, implication, and if and only if, right? These four, sorry I can't count, these four are binary connectives, this is a unary connective, and quantifiers. Exists at all. Okay, so my standard example, because I like fields, will always be the language of rings. Well, really, I mean the language of rings with a unit, unitary rings. So this for me is 0, 1, plus, minus, and times. And now let me try for colors. So these, that is very well readable, are constant symbols, 0 and 1. And maybe I need different colors, but plus and times I consider as function symbols which are binary. So you plug two things in, whereas minus I consider as a unary function symbol. This doesn't, I mean, you can also consider minus as a binary function symbol if you like, but so. And then maybe you want to add an ordering. So then you take the language of rings together with a binary relation symbol less or equal to. No, that's here. Sorry. This is a relation symbol and that's binary. Or maybe the language of order to be in groups when you want to forget about the whole, I mean, when you want to have less structure. This for me is 0 plus, and again, less or equal to. Or maybe you want to take also a symbol for a function called exp. So exp is a unary function. Really, I mean, presumably in one of our applications, the reals will feature as an exponential field, so. Or maybe something I like, which is the language of valued fields. I mean, I'm not saying I don't like any of these languages. Namely, so I usually consider a valued field in the language of rings, together with a unary relation symbol which unary relation symbol I would call O. Okay, so far these are just symbols. And now an L structure is a thing where we give, or is a set where we give these symbols meanings. An L structure consists of a non-empty set together with interpretations for each of the symbols. So let me try to do the definition by example, by what I mean by interpretation of each of these symbols. So, e.g., any ring is naturally, well, maybe any unitary ring is naturally an N-ring structure where you choose the obvious, right? Where you choose the obvious interpretations of all of these symbols occurring. But you, of course, you know, not every ring can be. I mean, not every ring is necessarily orderable in a sensible way. But however, I can turn any ring, I mean, into a structure in the language of ordered rings. Maybe the ordering is just nonsense, right? I mean, so. But also, any ring can be turned into an O-ring structure. Okay, now let me write it out in many ways. Let me write it out. So I look at F2, 0, 1, plus, times, minus. All of these I give the usual interpretation. And then I add an interpretation for my binary relation symbol. So, e.g., I can say with less or equal interpreted to hold for all pairs. So this is a perfectly fine structure in the language of ordered rings. It's not an ordered ring. I mean, it's not an ordered ring in the sense we know it to be, but it's good structure. Okay, so now we have a notion of structures. We get a notion of homomorphisms. Embeddings and isomorphisms. There's a subtlety here, so while I would like to write nothing more, I would just, I mean, you know, in an ideal world, you'd all now know immediately what I mean by well, in substructures. So there's a subtlety with homomorphism and embeddings. Embeddings are not just injective homomorphisms, so this is why I need to write the definition down once, even though you'd rather not see it. So substructures is just the obvious thing, right? I mean, you take a subset, and a substructure is a subset. If it contains all the interpretation, a subset supports a substructure if it contains all the interpretation of the constant symbols, and it's closed under the function symbols, and the relation symbols you just cut down. But for for a homomorphism, now you think of a homomorphism of, say, so a homomorphism must preserve structure, as you know from taking an abstract course in algebra. So a constant symbol and the interpretation of a constant symbol must be mapped to the interpretation of the constant symbol. The function symbols must commute with the homomorphism. But there's a subtlety in the relation symbol, namely, so A, B, and structures. The question is, does the relation symbol, is there an if and only if or not? So let me write it down and then use, so a map F from A to B. I write my L structures as Fraktur letters, and then the corresponding Latin letters are the underlying universes, are the sets on which these structures are defined. So in the homomorphism, if for all, well, let me write it down for constant symbols and then not for relation symbols. So if C in L is a constant symbol, so there are structures in the same language, that's important. Then I have F, sorry, capital F, of CA is CB. Similar for function symbols. I hope you forgive me, otherwise look at my notes. I'll happily make my notes available to you, and then you can. And so for relation symbols, so if R in L is an n-ary relation symbol, a homomorphic, say A1 up to AN are elements in A, then the homomorphism tells you that if A1 up to AN stand in relation with respect to this R relation symbols, then the same is true for their images. And now for an embedding, so this is the definition of a homomorphism, and now for embedding, you need an injective homomorphism with equivalence in 3. Aha, maybe let me just point out one thing if you've never seen this before. Right, I purposefully write for my logical connectives, I write arrows with 1 bar, and for my meta implication symbols, I write arrows with 2 bars. So that you can immediately see where we are. Okay, so now we have a concept of structures, and now I want to give so the next step is to give a recursive definition of formulae. Now this is really horrid, so let me try to define it by example, and if you want more details you need to read, I'm afraid. So get a recursive definition of L formula. Okay, so the crucial thing about formulae, so they're in a given language L, and they're finite strings of symbols. From L, so they're allowed to use all these function symbols, relation symbols.
Francesca?
Yeah?
Just a small thought. So you haven't mentioned that equality is always part of the language.
Yes.
So for the embedding that, this makes it 1-to-1.
Aha, no. Yes, so I tried to write it in a way. I tried to write it in a way that equality is not one of my set of relations.
Okay.
Somehow it's an extra labeled relation, but thank you, that's a very good point, right? If I meant here my relations in 3, they should be coming from the orange-yellow set of relations. Okay, so these are finite strings of symbols from L, and now I'm allowing equality again. And now I'm relying on you as a semi-computer, which makes sense. Which makes sense in the way that for any I'm relying on you being mature mathematicians, maybe, in the way that for any A structure A, phi and L formula, then you can plug elements of the underlying set, which is called A, into the variables of phi. Well, into the variables of phi which allow plugging in, i.e. which are not. I'll do it by example, then it's easier, but let me write down my vague definition first. Under the influence of a quantifier, okay. For any L structure A and for any L formula phi, you can plug elements into the variables which allow plugging in. And then you get a statement. So you get some statement which makes sense, which you can read as and the statement needs to be either true or false in your structure. Okay, this is very vague still, and I hope to define it by example, and then it will be less vague to you. So the crucial point is that my quantifiers may only range over elements, not over subsets. Quantifiers, because right, there's no symbol. I mean, quantifiers can not say there exists a relation symbol. That's not. I mean, because there exists a relation symbol is not something which I can. I mean, I can express in this way. Quantifiers only range over elements, not subsets. Okay, so definition by example. There is a y times y is equal to x. So this is now a formula, maybe in the language of rings. Right? It uses one non-logical symbol. Okay, maybe it uses. I've already switched from calling my variables vi to calling them x and y because I prefer x and y for my variables. Here it uses one non-logical symbol times considered a binary connective, or sorry, a binary function symbol, and of course this makes sense, right? And it can either be true in a ring structure or it can be false. But you can evaluate it by plugging something in for this x, right? You can see whether x has a square root or not. That's what the statement is, I guess. So this makes sense, and x is a so-called free variable because you can put something in. Now, while y plus y, this is what's called a term. This is not a formula because you can't evaluate it and get something which is true or false. Right? It's a building block for a formula, but it's not yet a formula, so that's not. Of course, something like y plus also doesn't make sense, right? I mean, now I'll immediately start using abbreviations. So if I look at, for example, the sum vix to the I from I equals 0 to n, this is now an abbreviation. I mean, well, like this maybe it's not a formula, so let me say it's equal to 0, so it becomes a formula. Okay, so I want to say this I will consider as a formula in the language of rings, And this works because there's finitely many plus symbols involved and finitely many powers. And the powers, of course, I mean, x to the I take as shorthand for x times xi many times. And for any fixed n, I could write down this. So
n is a number, not a variable. N.
Yes, you're right. N is a natural number. It's not a variable. It's not an element of my structure. It really somehow it's really an abbreviation for a finite sum. What I'm doing there. So. And the feature again, so let me give it a name. I call this formula psi-n now. Okay, so maybe another one.
So x is a variable?
Yeah, so here the variables are x and v0 up to vn. I'm cheating by using n plus 1 many variables. N plus 2, I guess.
So does it... I know you can apply for values for x for all elements in the vector.
Yeah.
To give different answers, true and false, depending on...
Yeah, so here you also need to plug in things for the VIs.
Okay.
And if you plug in something for every variable, then on the left-hand side you get a polynomial expression in one variable. I mean, with something plugged into the variable, you're evaluating a polynomial at a point. And so plugging something in would be plugging something in for all the VIs and for x. And then it's either true or false, right? Either this, you get something, either it's true that x is a 0, what you plug in for x is a 0 of the corresponding polynomial or not. So in order to not confuse, and I often write my formulas given by and then write equivalent to this is now a form. This will now denote a formula, and now I write down what the formula says on the right hand side. So this says another example. There is a z such that x is equal to y plus z squared, where again z squared is an abbreviation for z times z. This is still a formula in the language of rings. You can see, I mean, you can of course give many more examples of languages, and then, because I want to highlight number theoretic connections, I'll often work in fields, I'm afraid to say. Okay, so also because I like this. And now I want to look at the pairs. And I want to give this a meaning. I want to look at the pairs A and B from the reals for which this holds. Right? So, and this is, I'm denoting this by this, right? This means the reals interpreted with the interpretation of the ring symbols in the usual way entails row of A, B holds. And this implicitly means A and B are elements of row, of the reals. Okay? Does someone have a suggestion for which pairs A and B this holds? I mean, I'm sure most of you do, but is someone willing to give me a suggestion? Yeah.
A greater than or equal to B.
And then only if A is greater or equal to B, yeah. Aha, my notes even say A is less or equal to B, so good that I asked you. Okay, I want to say another thing I can express where I don't need any language, but I only need the logical symbols, the last 3 lots, is to say I have n many elements. So for a fixed natural number, I want to look at the formula chi n, which says, well, it will be a statement, so there's no free variables. There exist x1 up to xn. So these are really, again, I'm doing an abbreviation immediately, right? Really, these are n existential quantifiers one after the other. I've just already written them all as one. I hope you forgive my indiscretions. Okay, I want to say each of these two, they're pairwise different. So not xi is equal to xj. I guess I should just write I not equal to j. Okay, so this now tells me I have at least n many elements, right? This says that there are n many elements which are pairwise different, and now I want to say and everyone else is equal to them, so and for all y, I have y is equal to one of them. So this formula now holds in any structure in any language if and only if that structure has exactly many elements. Okay, final example. Need a bit more space, so maybe let me start my last line here. So now I want to look at the formula phi of x, which says there is a y squared is equal to 1 plus px squared. I'm doing the p-adic analog of the defining the ordering in the reals. We just defined the ordering in the reals, so what's the p-adic analog? I look at this formula. There is a y, what such that, so in other words, 1 plus px squared is a square. So what's p here? Okay, so let me say p prime for this to make sense. But what's p here? I'm interpreting p as 1 plus 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 1 p many times. Right? So in this way, in any ring structure, p makes sense as an element in my formula. Okay, now I claim that in QP believes phi of an element b, phi holds for an element b in QP if and only if b is a p-adic integer, i.e. the variation ring of the p-adic numbers. And for this to be really true, I should have taken p not equal to 2. Okay, so if you want to, first of all, what you need to do is p is, if you're interested in 2, then you replace squares by cubes, and all is still well. I guess this is what you now do. This is what you now do while I wipe the board. You calculate that this is correct. So to go from here to here, you imagine what happens if the value of b is strictly less than 0, and then you argue with parity. So by the fact that the value of p is the minimum positive element, so the value of px squared, of pb squared is odd if the value of b is negative. But I guess the value of pb squared is always odd. And for the other direction, you use Hensel's lemma. Okay, that's what you do now while I do the wipe. Okay, so what these examples, I needed to introduce to you what formulae are. But what these examples should tell you is that it's not unlikely that you can describe some sort of structure using first-order methods. Of course, we'll also see structure which is not describable or which is not first-order in further examples. Right now, we don't have means to say something is not definable by a formula, right? What I can prove right now is something is definable. The best means of saying something cannot be definable will be after this afternoon's lecture, when we've talked about quantifier elimination, which essentially just means understanding getting a precise understanding which sets can be described by first-order formula in a given structure. time. Any questions so far?
Sorry, I'm
Yeah,
still
yeah, please.
thinking about how to evaluate the third example to true or false given a structure. So is it right that you're saying this is just a polynomial in n plus 2 variables?
Yes, it's an expression in n plus 2 variables.
Okay.
And plugging something in means plugging n plus 2 many things in.
Yes.
And then what you get is either something, what you get is 0 or not in a given structure. And you calculate, you do the...
But I thought the true or false depends on which n plus 2 values you plug in.
Yeah? Yeah.
Whereas the other examples where you have an existential quantifier, that's true or false for a given.
Yes, the question is whether there's variables you can plug in still. Right, so for example here, if you plug in something into my, if you plug in a pair of reals into row,
Yes.
right, either the first is less or equal to the second, it's bigger or equal to the second, then it holds in the real, say, but it makes sense in any structure. Any structure where these symbols make sense. So whether it's true or false, yeah. Whereas this sentence, right, you can't plug anything in. But in all the others, I think you can plug something in, no?
So for the first one, that's going to be true, like if we're in the rationals, it's going to be true if x is equal to 4, but not true if x is equal to 3. But it's always true in the complex numbers.
So, okay, maybe I'll think.
Yeah, we can do an example in the break. We have a coffee break afterwards, if you like. Okay, so, I was talking about plugging things in. So if you can't plug anything in, we call it a sentence. And I also need the notion of a theory, namely a theory is just a set of sentences. Okay, sentences. So no free variables means nothing plugging. No plugging possible. So, theories which will feature today is the theory of fields, which is given by field axioms, which you can write down in the language of rings, and I will not write down the field axioms for you. Beware that 0 is not equal to 1 is one of the field axioms. That's the only subtlety there ever is about field axioms. Then I can look at field n, which says I'm a field, together with I have exactly n random elements. So, sorry, what was this called? Chi-n. So this is theory of fields with exactly n elements. Okay, maybe there are not so many fields with exactly n elements, and it depends on the. But we'll come back to that in a moment. So maybe a meta remark before I go on. So model theory is about the interplay of models and theories. So structures in the language of rings and sentences / formulae which hold in these structures. So this somehow, right? This is you've just seen the theory side of model theory, and the model side are these structures which well, which were erased already. And it's about the interplay between the two, and you might want to show something about the class of structures satisfying a certain theory to learn something about the theory, or you might want to show something about somehow syntactical properties of the theory to learn about the class of structures corresponding to that theory. So maybe you're interested in theory, maybe you're interested in structures. And this viewpoint changes all the time. So right now I have theories, and in the moment I talk about things which satisfy these theories. So another thing is I want to look at the a ring theory of algebraically closed fields. This is the theory of fields, together with the statement for every n that every polynomial in every non-constant polynomial has a root. Now I guess I didn't do the right abbreviation up there, so I guess that is. Can I salvage it from there, from the psi n? Right, I need to say for all coefficients. So for all v0 up to vn, there is an x psi n, where psi n really depends on v0 up to vn and x. And I need this axiom, I need one axiom of this kind for n. What do I need? Greater or equal to 1, maybe. 1 was right? I needed to be. Counting at the board is not so easy, even if it's just to 1. Yeah?
Will you have vn not equal to 0 and 5?
Yeah, I guess you're right. If I really want to exclude constant polynomials, I should have better say something about vn not equal to 0, right? Let me do that. And vn and not vn equal to 0. And this is one formula for every n greater or equal to 1. Right, because I want to exclude constant polynomials. That's really what Leo was helping me doing. Okay, so this says I'm a field, and every polynomial of degree greater or equal to 1 has a root.
You probably want to say that.
Yeah.
If vn is not equal to 0 implies that there exists an x.
Yeah.
Aha, you're right. I should have.
I think we understand.
Yeah.
Or you could do it that way too.
Yeah.
I think now, yeah, thank you. Okay. I also look at the theory of real closed fields, which will be, well, essentially the ordered field axioms. So field axioms together with less or equal to defines a field ordering, so it's compatible with plus and times in the appropriate way. And now I want to say, okay, so the field is called real closed if it's an ordered field, such that every positive element is a square. So for all x is y, x is equal to y, x greater or equal to 0 implies x is equal to y squared. And now I need to say, if only I'd done this a bit better, I need to say, I just write it down, I need to say every odd degree polynomial has a root. So, let's just write it. And you can, I'm sure you can now work out how to say this from this. Every odd degree poly has root. So this is called the theory of real closed fields. Okay, and now we've already talked about structures where these axioms may or may not hold, so an L structure A is a model of T, where T is an L theory, written A models T. A is a model if every phi in T holds in A. Holds true in A. If T has a model, we call T consistent. Okay, so clearly, for example, the field with p many elements is a model of the theory of fields with p many elements, yeah?
For you, are theories necessarily complete?
No.
Okay.
No, really not, right? I mean, it's just a theory for me is any set of L sentences. C is the model of the theory of algebraically closed fields. I guess so is FP alg. And the reals are a model of the theory of real closed fields. And now, I guess for now, if you also like, I mean, throughout the course, my running examples will be algebraically closed fields, real closed fields, finite fields, and p-adic fields. And so far, the p-adics, right, they're only a model of the theory of fields. I mean, if you follow Sylvie's talk, maybe you get an axiomatization of the p-adic fields. Okay, so now I need one more. So the question, right, is, well, if I have a theory, maybe there are consequences from this theory. This is the question of whether a theory is complete. I mean, or deductively complete. So a sentence phi follows from a theory T, and this is, right, this again means L sentence, and this is an L theory. If phi holds in all models of T. And in fact, if you take a course in model theory, or maybe even in first order logic, you'll learn that a sentence following from a theory is, I mean, that it holds in all models of T is equivalent to you can deduce it from T in the, I don't know, in some sort of Hilbert calculus or sequential calculus, but I'll only use this semantical notion here. I mean, right, T entails phi. And now what's complete? A consistent L theory T is called complete if it entails every sentence or its negation. If for every L sentence we have T entails phi or T entails not phi. Okay, so typical, in fact, only, so that's a spoiler, I mean the only spoiler of a complete L theory. Well, in a structure, I can just, for every sentence, I can check whether it's true or false. So, if I just look at the theory of an L structure, A, By this I mean theory of A is the set of all L sentences phi such that phi holds in A. And because in a given structure everything's either true or false, this is a complete theory. I guess we now have one example of a complete theory on the board. Okay, one example, we have several examples of complete theories on the board, but one where we can argue it. Namely, let's look at field n. So obviously we know field n only has a model if n is a prime power. So it's consistent if and only if n is a prime power, because consistent meant has a model. Can't see it on the board anymore here. If T has a model, we call T consistent. And now, but we also know there's a unique field of with p to the n many elements for a prime power p to the n. So in fact, the theory field p to the n is exactly the theory of the unique field with p to the n many elements. And that's complete. Because it's equal to the theory of fp to the n. Because that's its only model. I'll spoiler. Okay, the theory of real closed fields is also complete. And the theory of algebraically closed fields is complete once you fix the characteristic. I mean, obviously, whether 1 plus 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 1 p many times is equal to 0, that's the first order property, which, for example, holds in this algebraically closed field, and it does not hold in this algebraically closed field. So the theory of algebraically closed fields can, as it's written over there, cannot decide the characteristic, so we need to fix it. I hope I'll get to the end of this, proving that this is the only example of a complete theory today, so this morning. So for this I need the notion of elementary equivalent to L structures A and B are elementarily equivalent, written A is equivalent to B if they have the same theory, i.e. every sentence which holds in A holds in B and vice versa. Note, if you're isomorphic, so if there's a bijective embedding between you, then you're in particular elementarily equivalent. And the converse only holds for finite structures. I mean, that the converse holds for finite structures. If two finite structures are elementarily equivalent, then they're already isomorphic. You can somehow explicitly construct the isomorphism from the elementary equivalence, because the finite structure knows all its elements in some way, right? You can talk about in some sense, every of the n elements. That the converse does not hold for infinite structures, we'll see, I guess, this afternoon. I was about to say we'll see later today, later in this lecture, but that's a lie. Yeah?
For use, are finite structures finite universe, finite limiting relations, finite?
Finite structures means finite universe. It's nothing on the language.
Okay.
Finite structure means the supporting set is finite. Okay, final lemma. Let T be a consistent L theory. The following are equivalent. I guess I have to wipe before I can write it all. First, T is complete. Secondly, all models of T are elementarily equivalent. And thirdly, T is the structure of an L theory. So that's the spoiler of the example. There is an L structure A with, and now there's a subtlety, so that this set of sentences phi such that T entails phi is equal to the theory of A. Or in other words, the deductive closure of T is the theory of A, because maybe here I said up there, field N is field P is a complete theory, but of course you could write many more things which are true in the field with P many elements. And so now this is what takes care of the left-hand side here. That everything which follows from this theory is in fact what's true in FP. In other words, you can also say the theory of A and T have the same models. Every model of the theory of T is necessarily a model of the theory of A, and vice versa. That's a reformulation of 3. Okay, so which way am I going? From A to C, T is complete. Now I want to find the structure A. Let A be any model. If T is complete, I know it's consistent by definition of completeness, so it has a model.
Yeah, A and C, is this 1 implies 3?
The 3.
Aha, yeah, indeed, it's, thank you, it's 1 and 3. So if A says phi is true, then because A is a model of T, T cannot entail not phi. Because T entailing not phi would mean not phi holds in all models of T. But now T is complete, so this means T entails phi, because it must entail every sentence or its negation. Thus, the set of phi is such that T models phi is exactly the theory of A, is exactly the set of sentences which are in the theory of A. You might think I've only proven one inclusion, but note that the other inclusion is just if A models not phi, and it's the same line of argument. Okay, let's try to get from, well, that's not good, right? I should get away from 3. Let's get from 3 to 2. If there is an L structure, then all models are elementary equivalent. So if B is a model of T, then if 3 holds, B models the theory of A for the L structure A given me by 3. But this exactly means A and B are elementarily equivalent, because then exactly the same, I mean, every sentence which holds in A must also hold in B, but every sentence or its negation holds in A, so it already means A and B are equivalent. And finally, from where do I need to go? From 2 to 1. So what do I have? All models are elementary equivalent, and I want to show T entails every sentence or its negation. I guess here note that I've written consistent in the assumption, so let A be any model of T. If phi holds in A, all models are elementary equivalent, so then if phi holds in A, then phi holds in any elementary equivalent structure. In particular, it holds in all models of T, so T must entail phi. But otherwise, not phi holds into A, and then T entails not phi. So T entails every phi or its negation because every phi or its negation holds in A. So T is complete. Okay. Yeah, and this, as I said before, somehow the spoiler is RCF and ACF after fixing the characteristic are complete, but I can't prove that yet. I mean, I have no means of showing that yet. I guess this is what I wanted to say in the morning sessions. Thank you for bearing with me.